Okay, good afternoon guys. Good afternoon all of you.
Can you hear me?
Good afternoon guys. Good afternoon all of you. Welcome to YouTube channel of Chem Academy. So this is English only session of main group, Chem English session of main group chemistry. We will start discussing main group chemistry in this lecture. Hello, good noon to James. Gaurav Singh, thank you. Amit, welcome to the stream. Shrikant Chobe ji, welcome to the stream. Shweta Moria, hello, how are you? Okay, Chehal ji, welcome to the stream. Okay, we will try to finish it, and as soon as possible we will try to finish it. So this is main group session. Main group. In main group chemistry, we generally discuss representative elements, that is P block, as well as S block elements. So main group comprises of two groups priorly. One is your S block element and another one is your P block element. We will start from P block, and then in the later half we will discuss S block chemistry. That what we have to study according to your examination, whether it is your GATE examination or your, you can say, NET examination or JAM examination. We will cover the syllabus of these three topics, these three exams to be precise. Firstly, I will discuss P block chemistry and then I will go to S block chemistry in the later half of the subject. So P block basically starts from boron family, group 13. Right from group 13 we know P block starts. This is basically boron family, group 13. So in this family you are very much familiar with the elements. And after that, preceding group is your carbon group, carbon family. So in carbon family also you know all the elements pretty well, I guess. This much you know in periodic, according to periodic table you know the elements, that which element are there in this particular group. Later on it is followed by group 15, that is the nitrogen family. After that comes group 16, which is your oxygen family. And lastly there is group 17 and group 18. Group 18 is basically your halogens, your noble gases, and group 17 is your halogen group. So halogen group, priorly we have chlorine, fluorine, chlorine, bromine and iodine. And in noble gas group you know very well we have helium, neon, argon, krypton and xenon. So all these elements and their molecules, that is what we have to study during this particular course. Today we will start with our very first group, that is group 13, and we will see some basic, that how their molecule are formed, which type of properties are present in their molecule, what thing define their chemistry. If I talk about general electronic configuration of group 13, so general electronic configuration of group 13 looks very much similar to NS2NP1. There is only one electron in P orbital and there are two electrons in S orbital. And in excited state, if I talk about their electronic configuration, so I can simply write that this electronic configuration look pretty similar to NS1 and NP2. Only bromine is a second period element. So if it is a second period element, then I can say this is different from rest of the other in terms of not having a d orbital. There is no vacant d orbital in this particular element, no vacant d orbital, whereas rest of the element of the group have vacant d orbital in their valence shell. They have vacant d orbitals in their valence shell. Is this much clear to you? This is very basic I am discussing over here right now. This is the first lecture. We will try and discuss this group's chemistry, and first we will learn some various tools that will help us describing the chemistry of this particular group. How we can learn their reaction, how will their molecule be formed, what will be the basic properties of their molecules. Yes, definitely we will discuss it in Hindi also. Sorry for asking this question, but please sir, तो आगे कंप्लीट हो जाएगा प्लीज. यस, इट विल बी कंप्लीटेड गणेश, डेफिनेटली इट विल बी कंप्लीटेड फॉर श्योर. शुभम, थैंक यू सो मच, बट आई थिंक वी you are my student, not a fan, I guess. Harshal Balarji. Yes, definitely we will discuss it in Hindi. Definitely we will discuss it in Hindi. This one is for English session, and we will discuss it in Hindi also. This particular lecture I have taken in Hindi. You can watch that also if you find difficulty in understanding in English. So this will be more helpful for those people who are not familiar or not fluent in Hindi, who have little bit difficulty in understanding in Hindi, particularly people belonging to South India. They find Hindi a little bit difficult. Complete. Yes, it will be completed. Yes, Roy, definitely it will be completed. There will be more lecture coming in this series in English version as well as in Hindi version. We will try to complete it as soon as possible. Right? I am fine, Rahul. How are you? So this is clear. Is this much clear? In group 13, our general electronic configuration is NS2 NP1. In excited state we have NS1 NP2. All are unparalleled electrons, or we can say all electrons are singly occupying each orbital, whereas 1p you see will be vacant in them. By according to basic Lewis structure, if I go, for example, if I take boron over here, I will see only 3 valence electron, and if I consider that boron is going to make a covalent bond with its side substituent, any side substituent, particularly a monovalent substituent, so in that case what we will observe is that after sharing of electron also, its octet will never be completed. Its octet will never be completed. It can have maximum of 6 electron in its vicinity. That just means that there is no complete 8 electron in the valence shell. What we can say is octet is incomplete. Octet is incomplete in most of its molecule. In most of its molecule. In most of its molecules. Whenever it form molecule, you will see that group 13 element will not have complete octet. So I can generally say that most of these molecules are going to be electron deficient according to octet rule. According to octet rule, what I can say? I can say most of the molecules of group 13 element are going to be electron deficient. Now whenever I write this term electron deficient, I am basically saying 2 things over here, either one of them or both combined. What are those 2 things? One thing that I am saying is a molecule can be electron deficient if octet is incomplete. If octet is incomplete according to Lewis theory. If octet is incomplete, that means the molecule is electron deficient. It is having a urge for electron, more and more electron, so that more electron still can be filled in its valence shell. And another thing by electron deficiency means that the center atom of molecule have high positive charge. High delta positive charge. Both of these type are described as electron deficient system. Where octet is not complete, we will say that this type of vacancy in the molecule is known as orbital vacancy. And when there is a high delta positive charge on a molecule, that on the center atom of the molecule, that generally is defined as charged vacancy. Let us have a look at these 2 terms now, completely a more detailed version of these 2 terms. If I talk in detail about these 2 terms, what I will say that a orbital vacancy might look like this one. Have a look at this particular molecule. If I say that I have a molecule that is known as BH3, where there is not high electronegativity difference. Electronegativity difference between center atom and surrounding atom is not considerably high. It is not considerably high. This is not high difference of electronegativity. So if there is no high difference of electronegativity, what we will say that on center atom boron in excited state, we will see there is single electron present in 2s, whereas there are 2p orbital which are having 1 electron each. Let us mark them as px and py, and we will say that pz is still empty. These orbital will intermix to give new orbitals. Those are also known as hybrid orbital. And by now I can assume that all of you know this thing, that hybrid orbital form better sigma bond than that of pure atomic orbital. If this is the case that hybrid orbital form better sigma bond, these orbital 1s orbital and 2p orbitals will intermix to form new orbital. Those are also known as sp2 hybrid orbital, whose energy is going to be average energy of 2s orbital and 2p orbital. After this hybridization, these single electrons will lie in newly formed degenerated set of hybrid orbital, that is 3 sp2 orbitals, and we will still have a vacant 2p orbital of little bit of higher energy. This 2pz is still vacant over here. When hydrogen come near to center atom boron, who is newly hybridized, who is just hybridized to give you 3 new set of orbital, degenerate set of orbital, those are sp2 orbital having single electron in them. Hydrogen will come in proximity of this boron with its 1s and will overlap individually with these orbitals to form a molecule that is known as BH3. Even after formation of this molecule, what you will see that there is not a completion of octet, as well as there is a vacancy, which is orbital vacancy. This 2pz orbital is completely vacant. Valence shell orbital is completely vacant, and it is not even participating in mixing as well. And this vacant orbital defines orbital vacancy. This define orbital vacancy. Another vacancy which I just talked to you about is known as charged vacancy. And what is the key difference in them? Please have a note of this. If I talk about charged vacancy, in charged vacancy you can easily say that at first, if we look at a molecule, for example, we have a CH4 molecule. Now in this CH4 molecule, our center atom is carbon, whose electronic configuration is 2s2 2p2, and in excited state, if I talk about its electronic configuration, this will look pretty similar to S having 1 unpaired electron and all the 3p orbital having 1 unpaired electron each. This is the excited state. Now when these orbital undergo mixing and form new degenerate set of orbital, forming 4 sp3 hybrid orbital, each of these new orbital will be singly occupied by the prior electrons, and I can now say that around carbon there is presence of 4 hybrid orbital, and these hybrid orbital will be containing, one electron each. When hydrogen come in vicinity of carbon, come in proximity of carbon, it will overlap with them through its 1s having 1 single electron. And after this you can easily say that there is completion of octet of carbon, as well as electronegativity difference between carbon and hydrogen is not too high. If it is not too high, neither hydrogen nor carbon will try to attract the shared pair of electron towards themselves. Now, if I replace this hydrogen by some highly electronegative substituent such as fluorine, in that case, you guys know pretty well that fluorine have an electronic configuration of 2s2, 2p5, having 1p orbital singly occupied. This fluorine will come with its p orbital and will try to overlap with carbon through its p orbital, forming sigma bond with sp3 orbitals of carbon, forming sigma bonds with sp3 orbitals of carbon. Now also octet is complete, but the key difference over here is that we can easily say here electronegativity difference between carbon and fluorine is very considerably high, and when electronegativity difference is high, my more electronegative atom will attract this shared pair of electron density towards itself, and that will form a high delta positive on carbon. Carbon is having complete octet, but still electrons are far away from it, so it will feel some vacancy. Such type of vacancy is known as charged vacancy. There is electron on carbon, there is complete octet on carbon, but after completion of octet also, what we will observe is that these electrons are more localized on fluorine. They are more towards fluorine rather than towards carbon, and that makes this carbon having a high delta positive charge, and this type of vacancy is known as charged vacancy. Interesting thing starts to come from the point where we discuss or where we see such molecules having both orbital and charge vacancy. Now if you look at these kind of molecules, they will show you some interesting chemistry. Particular example of this type is basically BF3. If you have a look at BF3 molecule, just like previous case, boron will undergo sp2 hybridization, and after forming sp2 hybrid orbital also, this will still have a pz orbital which is vacant. So it is having orbital vacancy. For sure it is having orbital vacancy. Definitely it will have a orbital vacancy. It will have only 6 electron towards its vicinity, whereas its 2pz will be completely vacant. Now if fluorine come and starts forming a bond with this boron atom, what we will clearly visualize from this graph is that fluorine is highly electronegative, and due to high electronegativity of fluorine, this bonded pair of electron density will be more attracted towards fluorine rather than towards boron. This electronegativity difference, this high electronegativity difference between center atom and surrounding atom, will make boron have a high delta positive on it. Now along with this vacant orbital, there will be delta positive, there will be vacancy due to movement of these electrons. One thing, clearly visualize it. One thing is there that it has shared its electron density, and after sharing, these electrons have moved even far away from boron, and that will make it feel more vacant. So basically we can categorize molecule in 3 categories. Vacant, or you can say electron deficient molecule, in 3 categories. First category is your orbital vacancy, molecule with orbital vacancy. Another category is molecules with charged vacancy, and the third type of category that I am discussing is those molecules which are having orbital as well as charge vacancy within them. Do remember this. Is it clear? Is this much clear, guys? Please tell me in chat, is it clear to you or not? Can you visualize these 3 type of molecule? First one is those molecule which are having incomplete octet, but their side substituent are not much electronegative. Second type is those who are having a complete octet, but due to high electronegativity of the side atom, the electron are far away from them, so they will feel electron vacancy. And the third type is which are having vacant orbital, that is incomplete octet, as well as they are having electrons that are bonded pair of electron density pretty away from them. So such type of molecule, particularly this third type of molecule, will show you an interesting chemical behavior, and that interesting chemical behavior will define the property of group 13 molecule. Generally will define the property of group 13 molecule up to a larger extent. Have a look at this molecule. Boron, even after sharing, have lost control of its own electron, and these electrons have moved pretty much towards fluorine. Every atom, according to Lewis theory, have a tendency to undergo complete octet. Sir, for BH3 means B2H6 in sp3, not sp2. What I am saying, James Peterson over here is, I am just talking about BH3. If that exists, that is another matter. Why it does not exist, how it changes its structure, we will discuss that also. Just have little bit patience. I am just talking about, no need to ask, sir. Okay ji, why no need to ask? I must ask, then only I will come to know what is your response, how you guys are feeling, are you feeling good or not about this particular molecules. That is the only way of asking, that is the only way of interacting, that I ask you, you give me reply, right? So James Peterson ji, I will definitely come to your point is definitely valid, but here we are understanding things from the scratch, from the very basic, right? So there are very much, there are high number of people who have difficulties in understanding the basic, right? For Rockstar ji, yes, you can say that, you can say Rockstar, you can definitely say this thing that you have said in this chat. This is definitely right. So in this type of molecule, according to Lewis theory, where I will continue my point. I will say that according to octet rule, each molecule will try to have 8 electrons around every atom involved. And because of this orbital as well as charge vacancy, now it is even more vacant than our initial BH3 molecule. BH3 was vacant, but there was just a vacant orbital, there was no charge. These shared electrons were pretty much close to boron. Now these electrons have gone far away, so I will say that this molecule will be highly unstable according to octet rule. As such, in this particular scenario, I will say if there is nothing extra happening over here, this molecule will be highly unstable, as electrons have moved pretty much far away from boron, and if they are far away with a vacant orbital as well, this octet will be highly incomplete and this molecule will be highly unstable. What will they do to gain extra stability? How can this molecule gain extra stability? Now, because of this driving force of having a complete octet, what happen over here is, write it down please. Due to this driving force of having a complete octet, new type of, or you can say a type of interaction will start to occur. What type of interaction will start to occur? That is what we are going to discuss over here in this particular lecture. This type of interaction, what do I mean by this? If any atom is having less electron around its vicinity, it will try to gain electron. It want more and more electron. How it wants electron, why it wants electron, that is what we want to discuss over here. The driving force for its need to have more electron is basically your incomplete octet. It is having incomplete octet. So what boron will try to do, that it will try to seek a donor. It will try to find a donor who can donate its electron density, any electron density. So there are two options for this case. One option is that some another chemical species some another chemical species from outside will come and donate electron to boron. In that scenario also it will have electron density, it will feel that its octet is getting complete. The another way is that those atoms which are surrounding boron, if they can donate electron density to this boron atom, then also boron will feel that its octet is slightly completed. Its octet is slightly completed. So there are two choices. It can either gain electron by route A or it can either gain electron by route B. Which type of route does it follow? Now you have simple choices. You have very simple choices. Let us assume that everybody who is attending this class, they want to have milk today. They want to have milk today. They have high urge to have milk today. And in order to attain milk, there are two ways. One way is just go down the stairs of your house, be on the road and find a shop very near to you and buy some milk over there. Or another way can be that you go and buy a kettle, raise it for years and then you extract milk and then you drink. If you have a high urge to get milk, what you will choose? You will definitely choose the first route. Means general tendency of human being or general tendency of element are our part, basically we are part of element, you can say we are made up of elements. So the general tendency is to have our need satisfied within our vicinity. We don't want to go and search for things that much. What we want is we want stability, and for stability what is better, that we have a shorter route. Anything which is in the proximity, which is in our vicinity, we will go there, we will ask for that particular thing and we will attain it. That means generally 99% of us will follow one simple route, that we will go down the stairs of our house, we will find a local shop and we will buy some milk out there and we will satisfy our need. Similar thing boron does. What boron does is that it have a donor, it have a species which is having electron beside it, just beside it there is fluorine which is having 3 lone pair of electron. So boron will ask fluorine whether you are capable of giving me electron or not. If you are capable, I will not interact with some outsider. I will not interact with some outsider. You can relate it to yourself also. You have group of friends in college. Generally, you hang out with them. You don't go and don't go and watch movies with random strangers on the street. If you want to have a movie, if you want to watch a movie, you will never ask a random stranger and say, I want to watch a movie. Can you go with me? Can you be with me? You will not ask that. You will ask your friend who are in your vicinity. If there is somebody occupying your space in your vicinity, you will not go and find some random stranger for your vacant system, for your vacant life to be fulfilled, for your enjoyment or for your movie watching or for your any need. You want something, you want some money. There is nothing like that. So boron will also do the same thing. Boron will say that I have in my vicinity this fluorine is bonded to me, it cannot run away, so why not just ask fluorine that please give me electrons. So this fluorine will give electron, but why? There must be a reason now why fluorine is giving electron. So the reason for fluorine to give electron is that through this sigma bond and due to its high electronegativity, fluorine have acquired the bonded pair electron density towards itself, more electron density towards itself. Due to its high electronegativity, this bonded pair of electron density is close to fluorine. Due to high electronegativity, what we can say, high electronegativity of fluorine, bonded pair of electron density is localized on fluorine. And look at fluorine. Fluorine was already having 7 electrons in its valence shell. Now it shared one, bring one more in its valence shell towards more close to it. That will bring some delta negative to it. Definitely it will bring some delta negative. It is already highly occupied by electron density, and more negative charge on it will make inter-electronic repulsion. This more electron density, this extra electron density, this extra negative charge will make inter-electronic repulsion, and this inter-electronic repulsion will be responsible for fluorine to donate electron density. It will want that let us give some back, so that I don't have that much of negative charge, so that I don't feel that much repulsion, so that my electron do not repel that much. So this fluorine, due to this extra negative charge, delta negative charge, will try to lose some electron, will try to give some electron to boron. And when it give electron to boron, there is another problem starts created. How another problem is created? That whenever this lone pair of electron density is transferred to boron atom, there will be delta positive on fluorine. And you guys know pretty well, whenever there is a positive charge on highly electronegative system, it is not stable. So what fluorine does is that it give electron and then again take it back. It give electron, then again take it back. Then give electron, then again take it back. Whenever it give electron, it get positively charged, delta positively charged, so it take back the electron density. Whenever it take back the electron density, there is high negative charge, so it gives the electron back to boron. So this giving and taking will continuously be occurring in the molecule. And if this giving and taking, give and take is taking place, we will say that there will be transfer of electron density, but partially, not completely. Electron density will be transferred, but for some time, for just some fraction of second, then it will be taken back, then again transfer, then it will be taken back. So we will say that partial transfer of electron density will take place. Partial transfer of electron density will take place. Have a look at this, very easy it is to understand. And if there is this give and take phenomena taking place, we can say that this electron density is quite movable. It is not a fixed electron density. It is never fixed between boron and fluorine, completely not fixed. It is going towards boron, then coming back, then again going towards boron, then coming back. So what will we say? That this is not a fixed electron density. This is a movable electron density, not a fixed electron density. Not a fixed electron density. Fixed electron density. Not only this fluorine, each fluorine will keep on doing this. Whenever this give electron and when this take back, another fluorine will give electron density. Then this take back. Then another fluorine will give electron density. Then it take back. Some other one will give. So this give and take will keep on going on. And if this keeps on going on, that will definitely enable us to know that each time whenever we look at boron, one of the fluorine must be giving electron density to boron. One of the fluorine must be giving electron density to boron. Means each time whenever we look at the molecule, we will feel that boron is having an extra electron density, is having a complete octet. Such type of completion is known as partial completion of octet. Why partial? Because these electrons are not fixed. These are given and again taken back. These are given and again taken back, given and again taken back by side atom. Did you guys get this much? This is very important because when I will discuss this reactivity of these kind of molecules, these things will come into picture again and again, and then you guys should not be confused that how this electron you are transferring back, why this is getting back again, why this is attacking from this side only. This will add up to your knowledge. This is very basic and very useful. Did you guys get it? Say yes or no in the chat. Say yes or no in the chat. If you like it, then if you get it, then say yes. And if you are new to the channel, please consider subscribing the channel. Don't go without subscribing the channel. Such videos will be regularly updated on the channel. Regular live stream will be held on the channel for sure. So if you are liking it, you must be subscribed to the channel. Okay. Such type of bond. Have a look at this bond. This boron from sigma bond, I can also explain this fact in this manner, that boron from sigma bond is transferring electron density to fluorine, and fluorine is transferring back this electron density to boron through its lone pair. So this type of bond is basically in the reverse direction of our sigma bond. Sigma bond electron density is moving from boron to fluorine, whereas these lone pair are moving from fluorine to boron. That means this is in reverse direction, or we can say back direction. So such type of bond is also known as back bond. Another interesting fact about this back bond is that for bonding to take place, we know pretty much there must be orbital overlapping. There must be orbital overlapping. If there is no orbital overlapping, then it will be difficult for bond to form. Piyush Yadav, no, there will be Hindi lecture also. This is for English version. Hindi lecture will also be conducted on regular interval. Okay, English is better. Okay, thank you ji. English is better, then it is good. Have a look at this particular system. Bond can only be formed when orbital overlap according to our VBT theory. What VBT say? Bond can only be formed when orbital overlap. When orbital overlaps. Now have a look at this boron particularly. This boron just had a p orbital. That is also pz orbital. Px, py were involved in mixing. So I can say that the whole molecule, this triangular planar molecule is present in xy plane because it is formed by px and py mixing. So this whole molecule is in xy plane, and this pz is perpendicular to the plane where BF3 is present, where all these three fluorine and one boron atom is present. This pz is perpendicular to it. If this is perpendicular to fluorine or boron, we can simply say that for overlap to take place, there is only one way left, that is some sideways overlap must take place. There is no possibility of sigma overlap because this orbital is not directing towards the incoming group. If this orbital was directing towards the incoming group, then there can be head-on overlap. If this is not directing towards the incoming group, then there is only one possibility left, and that possibility is to do a sideways overlap. And when atomic orbital do sideways overlapping, we know that pi bond generally forms. So what we can write, due to presence of only one vacant p orbital, there is possibility of just a sideways overlap. There is possibility for a sideways overlap only. Overlapping only. And if only sideways overlapping going to take place, then we know that type of back bond. What type of back bond is formed? This back bond is essentially going to be a pi bond, and pi bond are generally formed by, or we can say always formed by, atomic orbital. These cannot be formed by your atomic orbital. Have a look at it also. What I can say, pi bond can never be formed by hybrid orbitals. No hybrid orbital can form a pi bond. This is what you have learned in bonding. So we will say that this is essentially a case of atomic orbitals. Note it down. This is another important point. This is very, very important point. Note it down. R synergic and pi bonding are equal in some sense. Yes, you can say that. In some sense, you can say that. Yes, you can say that. No issues in saying this, that it is a synergistic bonding. Yes, it is kind of, right? But key difference over here is that this is not a permanent transfer of electron density. This will be transferred and then again taken back. In case of synergistic bonding, particularly when we talk about a CO group, CO as a ligand, CO when donates electron density, it donates to a partial anti-bonding orbital, partial del star. SPZ, higher energy orbital, is having slight anti-bonding character, so it forms a sigma bond, through that gain extra stability, and then whenever it give pi electron density, then also it try to attain a little bit of more stability. So this is the key difference over here. Here they give electron density, then take it back immediately, because whenever fluorine give electron density, it will acquire positive charge, then it will take back the electron density to again have that negative feeling, and whenever it have high negative, it will again give the electron density. So this give and take keep on taking place, and in this give and take, So sometime fluorine, first fluorine give electron density, sometime second give, sometime third give. Overall, we will say that boron will have extra electron density all the time. Whenever we look at the molecule, all time boron will have some extra electron density. So now we know that this type of interaction is basically a pi-back bonding. This is basically a pi-back bonding. Now what we have to learn is that when and only when this pi bond will be formed. When and only when this pi bond will be formed. This is very important for us to understand. So write down in your notebook condition for back pi bonding to take place. Back pi bonding to take place. Bonding to take place. What are the conditions for back pi bonding to take place? First and primemost condition is there must be orbital plus charge vacancy. Orbital plus charged vacancy. Why I write orbital plus charge vacancy, I will explain it to you. Just give me a moment. Most of you must have get why I am writing it like this, not only orbital vacancy, I am writing orbital plus charge vacancy. Why I am saying this? Just have a look at this BF3 again and you will know the reason that why I am writing that there must be a presence of orbital plus charge vacancy. The reason is that if there is no charge vacancy, if there is no delta positive on the atom which is having a vacant orbital, then there will be no delta negative on the side substituent, and if there is no delta negative, there will be no interelectronic repulsion, and if there is no interelectronic repulsion, no donation of electron density will take place. There must be a motive now. If there is no motive, nothing will happen in the universe. If you do not have a motive of cracking an examination, you will not study seriously. If you are for the sake of just passing your time by looking at some video, you will find that your time is getting passed, you are having a good time, just a chill time. But if you have a motive of passing an examination, you will revise these things day in and day out. So that what fluorine requires. Fluorine, for donation from fluorine or from any electronegative atom to take place, there must be an extra negative charge. If there is no extra negative charge, there will be no interelectronic repulsion. No interelectronic repulsion, there will be no back donation. That is why I have written orbital plus charge vacancy. Why orbital is required? Because this electron density must go in somewhere, right? If there is no orbital for sideways overlapping, no pi bond will be formed. If there is no orbital for sideways overlapping, no pi bond will be formed. That is another key aspect to note down. This is very, very important. If there is no electronegativity difference, if there is no orbital vacancy, nothing can make a back pi bond. No molecule will make a back pi bond. That is another interesting key aspect that you must know about it. So this is the first condition. There must be orbital plus charge vacancy. Now this orbital plus charge vacancy is not only limited to center atom. This can happen when there is a delta positive on surrounding atom also. Write it down. This orbital plus charge vacancy. Can be present on center atom as well as surrounding atom. Basically, in simple language, you can write it down as there must be an atom in molecule which is having or who is having high delta positive as well as vacant orbital in it, and there must be at least one atom which is having delta negative and lone pair on it. which is having delta negative and lone pair on it. It can be either center atom or surrounding atom, doesn't matter, but there must be these two type of atom present within the same molecule. What two type? One atom having a delta positive and a vacant orbital, another atom having a delta negative and some lone pair, either one lone pair or two lone pair or three lone pair, doesn't matter. There must be at least one lone pair and delta negative on the atom, one of the atom of the molecule, and there must be a vacant orbital as well as delta positive on another atom. Do remember it. There are two driving force for this type of bonding. There are two driving forces. Driving forces for this type of bonding. There are two driving forces. First and primemost driving force is to complete octet. Octet completion is the primary driving force, and as well as you can say the second driving force for this type, particularly this type where there is incomplete octet, we can say second driving force for this type of bonding to take place is to decrease charge densities. Charge density created due to electronegativity difference. Created due to electronegativity difference. Electronegativity difference. Due to electronegativity difference. Negativity difference. Did you note it down? Did you note it down? Did you guys get it or not? Tell me in chat, quickly in chat, yes or no. You can type just Y or M if you are thinking that it is a hectic thing to study here. They keep on asking, did you get it or not? Will BF3 never react with nucleophile? No, it will react definitely, Rockstar. As I already told you, this is a movable electron density. So movable electron density means that there will be some time when boron will be having an incomplete orbital, at least some fraction of second, and that fraction of second is enough for nucleophile to attack it, but nucleophile should be highly reactive. Another point to note down. That is why I am saying that keep on listening these basic things very carefully. This will help you understand the reactions particularly. Another important thing to note down over here is that this type of bonding is present in charged species. Charged species yani those charged species which are having a delta negative as well as a delta positive. If there is no charges, there will be no such bonding. That is another key important aspect that you must note down from here. For such type of back bonding which is happening for octet completion, driving forces are primary octet completion, and second one is the decrease of charge density which is being created by electronegativity difference. If there is no electronegativity difference, that means second driving force is missing. Such bonding will not take place. Such bonding will not take place. To decrease, sir, you write no. Oh, sorry, my mistake. To decrease, no decrease, need to decrease, which is to decrease charge density created by. Okay, so that is now corrected. Thank you for the correction very much. Thank you very much for the correction. That just I wrote it in the flow of the thing. Now, another important question rises from here is that does this type of bonding only occur in species having an incomplete octet? Does this is the question which I am asking you. You have to give me answer. You have to give me answer. Everybody have to give me answer. Does this type of bonding occur only in molecules having incomplete octet? If no, then what is the driving force? You have to answer this. What is the driving force? Tell me your answer. Niche wala point. Okay ji, I will repeat. Which point? I am saying that there must be at least an atom having a delta positive and a vacant orbital, and at least one atom in the molecule which is having a delta negative and electron density on it, means lone pair of electron density on it. That is what I said over here. Now the question arises from this particular thing that we have learned so far. I am saying that does this type of bonding only occur in those molecules which are having an incomplete octet? If no, If no is your answer, then what is the driving force? You have to answer it. If yes is your answer, then no issues. You just know that there is no such bonding in other type of molecule. That may be right or you may be wrong. That I will tell you just in a short while. Before that, please try to answer it. Everybody who is watching this, all 50 students must try to answer this. That does this type of bonding is to attain the octane? I am saying, does this type of bonding occur only in molecule having an incomplete octet? For molecule having incomplete octet and differences in electronegativity, we know that this bonding occur. That is what I told you right now. But I am asking that if there is a complete octet, can such bonding occur there also? And if this occur, then why does it occur? What is the reason behind it? So two of you are saying that this will not occur. Yes is saying not occur because force is to stabilize electron through delocalization. Oh, okay. So you are saying that force is to stabilize. That is the second case. Second case. That is second case, not the prior case. Another one is no sir, vacant D रहने से भी होता है, वेकेंट ऑर्बिटल से भी होता है, ऐसा बोला है किन्होंने? दिस इज सेड बाय उपासना. ओके, अवेलेबिलिटी ऑफ डी ऑर्बिटल कैन मेक सच बॉन्डिंग. ओके, दिस इज सेड बाय मुकेश. बट ओनली अवेलेबिलिटी, इज दिस द ड्राइविंग फोर्स? नो, दिस इज अ रीजन that there is a vacant orbital, some d orbital or some f orbital, so they can attain electron density and blah blah. That is the explanation to the thing. What is the driving force behind it? Caused by electronegativity difference. Okay, have a look at it. The answer is yes, this type of bonding can occur. Yes, this type of bonding can occur in molecule having complete octet already. This can occur in molecule having complete octet already. But driving force, what is the driving force? The driving force for such bonding to occur in molecule with complete octet is basically to reduce steric repulsion. Steric repulsion, that is the primary driving force. And another driving force for such bonding to take place, second driving force is correct, as most of you have said, is to neutralize the charges created by electronegativity difference. Electronegativity difference. So most of you did not know about this. I was expecting few of you to know about it. That the second type, that this type of bonding in molecule with complete octet only occur to reduce the steric repulsion. This is the main reason. Primary reason that occurrence of such type of bonding is basically due to reduce the steric repulsion over here. Now, how does steric repulsion affect? Have a look at some other molecule. We will discuss one more molecule over here. Let us consider we have NH3. This is very interesting molecule. This molecule is highly interesting. You have studied about it in bonding also. That when we study its bonding picture, its hybridization picture, what we used to say is that let us assume that this is the nucleus of our nitrogen atom. Here somewhere will be 2s, more close to nucleus, and 2p will be little far away from the nucleus as compared to 2s. So if I plot an energy curve, the energy curve will be inversely proportional to the distances of orbital from the nucleus. The orbital which is more close to nucleus will feel more attraction, its energy will be lowered, whereas 2p will have higher energy. Now what we used to say over here is that if hydrogen come and start bonding with nitrogen from 2p, they will have a 90-degree angle. This is a little backstory that we need to know before knowing why this type of bonding occur. In this scenario, what we used to say is nitrogen is a small atom, and when hydrogen form bond to it at 90 degrees, the distance between the surrounding hydrogen will be very less, and this will be cause for a high steric repulsion. There will be high steric repulsion, and if there is high steric repulsion, molecule will be unstable. Molecule will be unstable and will not be formed like this. It will not be formed like this. So for the formation of NH3, what we used to say that there should be sp mixing, and with this sp mixing there was formation of this new sp3 hybrid orbitals, 4 sp3 hybrid orbital having one lone pair and another 3 unpaired electron. Now these sp3 hybrid orbital used to bond with hydrogen, but with this bonding picture also what we used to say is that newly formed orbital always have energy to the average of these 4 orbital. 3 orbital higher energy, 1 orbital lower energy. So I can say that newly formed orbital will have energy close to 2p, and when they have energy close to 2p in this type of bonding state, what we used to see is that at room temperature these electrons used to gain energy and used to change their nature from sp3 to pure p. That is why we always study that our NH3 will show Walden inversion, and it will change its hybridization from sp3 to sp2 because of this low energy gap. A phenomena similar to quantum tunneling will be observed, and our hybridization of nitrogen will be changed from sp3 to sp2. We know this thing, right? We know this thing. This much we know about NH3. Now imagine this particular scenario. In NH3, what we say that the angle is around 107 degrees. Now let me replace these hydrogens by some big surrounding atoms such as SiH3, some big surrounding molecule, or you can say group. When SiH3, such a big surrounding group will come, this 107 degree angle will not be capable of reducing the steric repulsion. Here steric repulsion will be high. Imagine this. Hydrogen were small, at 90 they were repelling, at 107 they were not repelling, they were having some high distance. Now I replace this by some large group, this hydrogen, again steric repulsion will start to generate, and if this steric repulsion starts to generate, this angle will be stretched, and this bond will be stretched, and angle will be more, and in that scenario we will say that this angle will be greater than, this angle theta will be greater than 107 degrees for sure, 110% for sure. Two geometries, one is sp3, one is sp2. One is having 107 degree angle, another one is having 120 degree angle. These geometrical changes are observed at room temperature. If somebody want to learn it in detail, they can always go and find bonding lecture by Ved sir, that is already present on YouTube. You can go and watch this phenomena completely. He have taken one lecture, whole lecture on this phenomena only. Now this difference in energy of two states depends on, you can write difference in energy of sp3 and sp2 depends on bond angle difference. Lesser the bond angle difference, more easy it will be for molecule to change its geometry, from tetrahedral to triangular planar. This phenomena will start taking place at low temperature also. Do remember it. Bonding nature is same. There is still a lone pair. If it gain temperature, it will go into P. Definitely it will go into P. there is high steric repulsion at 107 degree angle will be raised. When this angle will be raised, there will be less difference between 120 and angle greater than 107. Here the difference between the angle is 13 degrees. In case of SiS3, this difference will be definitely less than 13 degrees, and if it is less than 13 degrees, then it giving small amount of heat or small amount of temperature will change its geometry from sp3 to sp2. Definitely it will change, and whenever this change occur, what we will see now, we will say that these two large group will be present at 120 degrees angle. And if this is the case, then what this molecule will try to do, that it will not go into sp3 back, because if it tries to go into sp3, it will have more repulsion. It will have high steric repulsion. Then what will you say? That in 120 degrees, this SI will avail its 3D, and this 3D will be responsible for taking back this electron density from nitrogen. And if there is lesser lone pair electron density, or we can say if these electrons are captured in this state, when they are in P, they will never go back to sp3. And this type of back bonding, we can say this type of back pi bonding in molecules having complete octet. Si was having 8 electrons, nitrogen was having 8 electrons, still there is back pi bonding, because this back pi bonding, what it does, it increases the bond angle, it decreases the steric repulsion. So the key driving force over here is to decrease steric repulsion. Did you guys get it or not? Tell me fastly. Then we will move on to another section of this lecture, and we will sum up whole thing which we have learned so far. That will make this theory be more resilient in your mind. You will be able to grasp it a little bit more. Did you guys get it or not? Tell me in chat. Too fast, please. If you guys get this phenomena, then why this type of bonding is occurring? There is no need of octet completion, no need at all, but still this is occurring. Why it is occurring? Because this molecule is having high steric repulsion in its normal bonding state, so it wants to increase the angle. And how it can increase angle? It can only increase I know this explanation, but was unable to remember. No issues, James. No issues. Then what is the driving force in case of phenol? Back bonding in case of phenol molecule and octet is complete as well. Rockstar have asked a great question, that in case of phenol, what we observe is that there is a back pi bonding. Yes, there is a back pi bonding. Phenol, Rockstar, the thing is, buddy, that whenever I say please focus, you focus. You must focus. I have already told this also to you guys, but not in exact fashion, but in some hints that I have given you, that whenever there is a formation of pi electron, pi bond, these electrons are never fixed. This is not a fixed electron density. Pi bond are not a fixed electron density. They are movable. And if they are movable, that means there is always some vacancy. There is always slight vacancy into the system. In case of phenol also, if you observe that carbon is forming pi bond, the carbon with which oxygen is bonding, it is already forming a pi bond, and this pi bond is movable, and if this moves, it will create orbital as well as charge vacancy on this carbon. Remember, pi electron density is never a fixed electron density. So we never say in a conjugated system having a tendency of pi electron to be moved, we will never say that there is completion of octet. We will never say this phenomena. Generally what we will see is that if electron density is pi electron density, then it can be easily moved, then there will always be vacancy, whether it will be for small time, for small fraction of second, and that vacancy will create this pi electron density to form a pi bond. You will not say that it is a case of solidly completing 8 electrons. It is not having 8 sigma bonded electron density. Do remember this. What VBT says, sigma bonded electron density is fixed. It is fixed between two nucleus. It cannot be moved. Pi electron density can be moved, and if it moves, that means That means there will be some sort of time, some fraction of time where octet is incomplete, and that fraction of time is enough for oxygen to donate the electron density back to your carbon. That is the reason for back pi bonding to take place there, right? Is it clear now? And if it is clear, then it is again, then we will move now, we will move forward. So Rockstar, is it clear? So that is why I am saying that here each and every single word of this lecture very carefully. This will clear most of your doubts. Many doubts will be cleared over here. Many doubts will be cleared over here. Okay, got it. Awesome, sir. Okay, ji. Thank you, ji. Thank you very much. Kailamba ji. Thank you very much. So by far we know that there are two types of back bonding that can occur. One is for completion of octet and another one is for decreasing steric repulsion. Another one is for decreasing steric repulsion. One is for completion of octet and another one is for decreasing steric repulsion. These two types of back bonding will generally occur. We will learn one more constraint that is applied on pi bond. For pi bond to form or to be more stable, what we generally know is that only three types of bonding is favorable. Three types of overlap will give us strong pi bonding. What is a bond? That is also one thing that you must know before studying all these things. What is a bond? Bond is basically an interaction that decreases system energy. If the bond is not decreasing energy or not decreasing energy as expected, what we say that these interactions are poor. One example for this which everybody will understand, I think 11th 12th student will understand also, that when we talk about nitrogen form 3 bonds with similar nitrogen atom, whereas we never say that phosphorus form 3 bonds. Why we don't say it? Because we say for a single phosphorus bond, the bond energy is around 140 kilojoule per mole, and when we see P2 molecule, this bond energy is definitely only around 280 kilojoules. This is not even thrice of what we expected for one single bond. If there is 3 bond formation, at least the energy must be thrice. In case of nitrogen single bond, we say that the bond energy is somewhere around 160 kilojoule, whereas if we see the molecule, this is around 1200 kilojoules. Thrice of 160, or you can say 200 thrice is basically 600 kilojoules. This is twice the expected energy. Means extra stability. Nitrogen is getting extra stability because of these two pi bond, whereas phosphorus is not getting any extra stability. Not at all getting any extra stability. Even the sum of 3 sigma bond energy is more than that of 1 sigma and 2 pi. So we say there is no pi bond formation. In case of phosphorus and phosphorus system, there is no pi bond formation. Only sigma bond formation take place. From here what I can conclude is bond will be called bond only if. Bond will be called bond only if we have, this is just an example, I am just giving you a number example. Bond will be bond only if it's provide extra stability to the molecule. If by formation of bond or by overlapping there is some extra stability gained by molecule, then we will call it a bond. And it is generally observed that for pi bond to form, for pi bond to be formed, or we can say a better pi bond will be formed only when we observe two type of overlap. These three type of overlap are 2p2p overlap, then there is a 2p3p overlap which can form a pi bond, and then there is a 2p3d overlap which can form a stable pi bond. And the order of stability of pi bond is basically dependent upon the principal quantum number and type of orbital involved. P orbital will form better bond than that of d orbital because d is more diffused, p is less diffused, and when principal quantum number increases, diffusion increases, so bonded pair electron density decreases. So what we can say by this, that pi bond formed when pi bond, or you can say stable pi bond will be formed by these three overlaps, and this will be the order of energy of pi bond formed. A pi bond formed by 2p2p overlap will be the most stable, then there will be 2p3p, and then there will be 2p3d. There is only one exception to this one. Only one exception to this particular rule. I will discuss that exception to you also. Otherwise, we will say that for a stable pi bond to be formed, there must be 2p2p overlap, or there must be 2p3p overlap, or there must be 2p3d overlap. Rest of the pi overlapping interaction are generally considered to be not very stable, and if they are not very stable, we will say they will not provide high stability to the molecule, and if they are not providing high stability to the molecule, we will not consider them as a bond. We will consider them as a weak interaction. Means if you you see anywhere 2p 4p overlap, you will say that this is just a weak interaction, this is not an extra stability which is gained by a bond formation, so that is very important for you to note down also, that generally three type of pi bond we will study. These are 2p formed by 2p overlap, which will be the most stable. Then there will be 2p 3p overlap, which will give us a pi bond which will be stable enough but little less stable than 2p 2p, and lastly we will have a 2p 3d overlap. So summing up all these things, we can say that about back bonding, we can say few things, we can note it down. All these things which we learned in this lecture, we can say essentially about back pi bonding is first and foremost thing should be according to this overlap is a back pi bond will be formed due to three type of overlap, because it is a pi bond, so we will say only three type of overlapping will be responsible for formation of pi bond. And order of energy of back pi bond will be 2p 2p will be most stable. Then order of stability, you can write order of stability, energy and stability is one and the same thing. 2p 2p will be most stable, then there will be 2p 3p, then there will be 2p 3d overlap. Only these overlap will give you a back pi bond. I can also write the whole statement, same statement in different language. I can say that back pi bond will be formed if donor, the atom which donate electron density, or acceptor, the atom which is having a high delta positive and a vacant orbital. Donor or atom, either one of them, is from second period. At least one of them must be from second period. That is only the case when 2p will be involved. For back pi bond formation, there must be one 2p at least, and that will be only possible if either donor or acceptor is from second period. The remaining one, the other atom can be from second period or third period. Now this is one and the same thing which I have written, just in another language I have written it. The reason HOI not a very strong acid, only inductive effect to determine acidity of HOF, HOCl, HOBr and HOI. I will talk about it, James. Just wait a second. Just let me finish this overview. Then I will come to your question. Don't worry. I will come to your question. No issues. This is oxo acid, right? And on oxo acid, there is some different concept. I will tell you. Don't worry about it. I will tell you. So this is one statement that I can write. Another statement that I can write about back bonding is, there are basically two driving force for back bonding to take place. We can write it down. Back pi bonding will either occur to complete octet, or to decrease steric repulsion. This will only occur in molecules having a orbital plus charged vacancy. That is a key important aspect. Another important aspect over here is, fifth point to note down, there must be lone pairs on donor atom. There must be lone pair, at least one lone pair on donor atom. And by this study, I can classify this back pi bonding into two ways. Type of back pi bonding. Back pi bonding, I can classify them into two manners. First manner is when back pi bonding occur from surrounding atom to center atom, and this will be generally observed in cases where octet is incomplete. To complete octet will be the driving force for such back pi bonding to occur. Another way I can categorize it in, the second way is going to be your from center atom to surrounding atom, and generally this type of back bonding occur to reduce steric repulsion. Generally this type of back bonding occur to reduce steric repulsion. Let us have a look at some key features about these two type of back bonding also. First, I talked about from surrounding atom to center atom in this lecture. Only I just told you from surrounding atom to center atom, that means our center is acceptor and surrounding is donor. Example for this particular case is BF3. In case of BF3, boron is having a vacant orbital, that is the center atom is having a vacant orbital, and my surrounding atom is having lone pair of electron density, and this is a second period element, so I will say that lone pair is present in 2p and we have a 2p vacant. So because of this 2p overlap, there can be a back pi bond formation and there will be a back pi bond formation. If I do not consider back bonding, if back pi bonding is not considered, if I do not consider back pi bonding at all, I will say that the initial hybridization of boron was sp2 hybrid it was. And if I consider back pi bonding, then also its hybridization is sp2. There is no change in hybridization because 2p is involved in pi bond formation. Another key thing I can say that if I did not consider back pi bonding, the bond angle was 120 degrees, and after considering the back pi bonding also we are having 120 degree bond angle. The only difference that back pi bonding will make is bond length will be shorter because of back pi bonding. This is the case that we will discuss over here. Why? Because back pi bonding will increase our bond order from 1 to some higher value, not even completely 2, but from 1 to some higher value. The bonding, we can say bond order will be increased. Second case I discussed in this lecture is the back pi bonding which occur from center atom to surrounding atom. Example to this I took was your MSiH3. Here octet is complete, but there is high electronegativity difference, delta negative on nitrogen and delta positive on Si, and this Si have vacant 3d also, so because of 3d 2p overlapping, there can be formation of back pi bond, and when there will be formation of back pi bond, what changes will be followed, we will have to discuss it. If we do not consider back pi bond in this particular case, what we are going to say is that initially the hybridization was supposed to be sp3 and angle was supposed to be near about 109 degrees, because angle cannot be more than 109 degrees in case of sp3. But if we consider back pi bonding, which is basically from center atom to surrounding atom, in that case we will say hybridization will have to change. Lone pair should go in 2p because only atomic orbital form back bond. No hybrid orbital can form back bond. For back bonding to occur, for angle to increase, for steric repulsion to decrease, nitrogen have to change its hybridization from sp3 to sp2. From sp3 to sp2, then only the angle will increase to 120 degrees. Means in this process I can say my hybridization index decreases. I value always decreases. And this decrease of I value will be correspondent to the fact that what is the amount of angle increased. I will come to that point also. Here also bond length will decrease because of pi bond formation, bond order will increase. So we will say bond length will decrease because of additional pi bond character, because of additional pi bond character. Now is this whole thing clear to you guys? I have summed up the whole lecture, whatever we studied in 1 hour 15 minutes. I sum it up in front of you, right here in front of you. Is this much clear? This is the base that we will keep on building on it. This is our base where we have to build and stack our building of knowledge regarding main group. So is it clear or not? Can you tell me in chat, is it clear or not? Give fast reply in chat if you think that I have made you understand this topic, then please reply by yes. And then I will come to James' question. James said that HY is not a strong acid, whereas your okay, yes, very good. Yes, it is clear. Very good, nice. Let's have a look at HOI case. This is separate. This is not from this topic. Just for James, I am saying that he is asking me that if we have HOI, we have HOBr, we have HOCl, and we have HOF. That why we are saying that HOF is most acidic, whereas this one is least acidic. So these are basically oxy acids. Oxy acids. In oxy acid, how we determine the acidic strength is by two factors. One is by looking at oxidation state, and second is that oxy acid acidic strength is directly proportional to number of OH, and it is inversely proportional to double bonded oxygens, right? It is inversely proportional to double bonded oxygen. So what we are going to say is, this is, I think I wrote it a little bit, yeah. What is it? It is, first factor is electronegativity of center atom. Second factor is number of, directly proportional to number of double bonded oxygen. That is what I wrote from over there. And the third factor is, it is inversely proportional to number of OH. Now in this case, what you will see is that there is only one OH group. There is no such thing such as double bonded oxygen, and each center element is having a delta positive on it, except for fluorine. Fluorine is having a delta negative on it, right? Because it is highly electronegative. So we will have delta positive on oxygen, and when oxygen is having delta positive, the electron pair from oxygen hydrogen bond will be extracted by oxygen, and it will easily liberate H positive. More easy liberation of H positive, more will be the acidic character. That is the answer to your question. This is the way of describing. This is not simple mineral acid. If we were talking about mineral acid, that will not depend on the electronegativity. That will depend on the bond distance. Wherever the bond distance is high, that bond will break easily, and more H positive and fast H positive will be liberated. James, this is for your particular question, right? So if you are having OH group, how will OH group liberate H positive? That will depend on two factors. One, what is the charge on oxygen, and if there is positive charge, it will liberate fast. If there is negative charge, then the thing which will determine is the stabilizing factor. Like Cl is having 3D, it will stabilize negative charge. Of oxygen if oxygen liberate H positive, which it will ease the release of H positive by stabilizing O negative by providing it its wicked 3D. 3D 2p pi bonding is very stronger than that of 4D and 5D case, so it will be second highest acidic. Then the later will follow. This is the exact reason, chemical reason behind it, beside learning these facts, right? So that is how you answer this type of question. So if this lecture was helpful to you guys, please do consider sharing it with your friends. Share it with your as many friends as possible. Anyone tell me this for DUBHU? Yes, it will be helpful for DUBHU. Om Prakash. Why anyone? I will only tell you. I'm here for telling you the answer. If you guys like this session, please do consider sharing it with your friends, as many friends as possible. And if you think that this session should continue, there should be more main group session. So please do come in a good number. Always we will interact. Is this lecture suitable for UPSC? That depends on Rockstar, that how much you have written. The key difference in UPSC and in other examination is your writing skill, not about knowledge. UPSC question are not that much difficult. The thing which matter is, have you understood the concept behind it properly or not? If you have understood the concept behind it properly, then you will be easily able to write down the answers, and if you write down the answer in a proper manner, then it will be more useful for you guys. Okay. Thank you, Om Prakash, very much. Thank you very much. Okay, James, sir, got it. Thanks. Okay, James, it's nice that you got it. We will be discussing such questions, as well as we will be taking such session on regular basis. Every day 2 p.m. you will have an English session. Every day 4 p.m. you will have a Kitab Nama. Those two sessions are fixed for now. Please do come in each and every session, no matter who is taking the session, who is the teacher, who is taking the session, what session it is. It will be helpful for you. Come in a good number, join us, and do share this channel with your friends who are still not our subscriber. Ask them to subscribe the channel, help us grow. We will help you grow in terms of knowledge. Thank you so much for joining, and if you really like it, please press the like button as well as the subscribe button. After subscribing, please click all notifications so that you will be notified wherever we come live. We will bring more session. We will fix more session. There are multiple sessions on YouTube that are there, but we will fix the timing like this. What about electro? Electro will be continued. No issue about it, Sheikh Imran. That will be continued. This that is about to achieve its completion. We have already covered halfway. We are on Nernst equation in electro. We will start discussing its application, and then there will be concentration cell. So before that gets over, we have started main group also, so that we will alternatively, or I think 2 lecture of main group or of electro, something like that will be there. Okay. Thank you. Where will be the next session? The next session of main group maybe after a day or a day before that, a day before or after that, right? So it may be one day after today, or maybe 2 days after today, right? Thank you for joining. Thank you very, very much for joining. Keep sharing, keep subscribing, and we'll see you with another lecture on the same channel with another live stream. Thank you for joining. Thank you very, very much. You must be here. You are छुट्टी